Hello, everyone. Hey, this is Professor Mohan here. Welcome to this first remote class session. Um, I know it's a different setting for us all to interact through this new remote setup. Right? Um I hope all of you are able to hear me well, loud and clear. I will test this clip again towards the end and make sure to record it again if needed. Also, I hope everyone is staying safe and healthy. And don't hesitate to let me know if I can be of any help to you during this difficult time. Um, Also, I would like to thank you all here for your cooperation and support during this remote learning process. Um, thank you for your cooperation and support there. If you have not done so already, I also like to ask that you take a minute to read my general outline email or the Slack message that I had sent earlier this week. Um, I know that most of us would have, got a chance to look at that email or Slack message. But for those who have not done so already, I recommend that you would take a minute to read through that, the general outline, and reach out to me if you have any questions. Right. A couple of quick reminder there. If you have any questions related to the grading, feel free to send me an email. I would make sure to check my email regularly and respond to you as early as possible for any grading related questions. Also, please make sure to see my note related to my virtual office hours. Just to follow up on that, I would like you guys to schedule virtual office hours, like the same process that you guys have done earlier. Just would go to my website and then click on the meeting, schedule meeting link, which would take you to the Google calendar and then schedule it that way. Except that this time we would meet remotely, right? So thereby I would be sending a Google Meet link to those individuals who had scheduled the meeting through Slack before our meeting starts, right? All right. Well, in this short clip here, we will get started with the red black trees. I would mainly go over the slides and explain a few important concepts such as rotation in red black trees. And towards the end here, I will introduce us to the exercise problem, and then I might ask you guys to work on it remotely at that point. Okay, so let's get started. So, firstly, you could access the slides for today from our course webpage in 202. If you would go to the lesson 13, balance tree algorithms, module 3, and then if you would go to part 1 folder in the Google Drive, you should be able to access these slides. So I recommend everyone to go through the slides and carefully review the um, content listed in the slides. And this is going to be a short clip where I would briefly go over, some of the important highlights in the slides, right? So it's not going to be a detailed video, so it's going to be a short clip. And then I would ask that if anyone has a question, to follow up with me through Slack or email, and then if needed, we can also make an arrangement to meet up with you through Google Hangout or Google Meet, right? All right, well, let's get started here. Firstly, we have been talking a lot about balance trees. In the first two modules, we looked at what we call as a 2 to 3 tree, right? So, just a quick recap, a 2 to 3 tree was a balance tree. It's a binary search balance tree, which allowed us to do a better search, a better insert, and better delete, right? So, it's all big of log n. Um, and the height of the tree was log n. But then there is a limitation with this approach, is that there's too much balancing that one would need to do. If you remember, we had a structure like this where we had um, three keys, right? So we would need to do a lot of shuffling around and a lot of balancing act. So that makes insert operation take really longer time, right? So that's the limitation with 2 to 3 trees. Hopefully we want to address that limitation by looking at a different tree in red black tree, and hopefully we can do a better insert, right? And then better in terms of balancing, so we don't need to do too much balancing as such. So a red black tree again is a variation of BST, and the tree is just going to make it a self-balanced BST, right? So it's a self-balanced BST similar to the 2 to 3 trees that we looked at, right? So it's exactly similar to the 2 to 3 trees, right? But then this time we are going to hopefully provide a better balancing act, and our aim here is to reduce too much balancing, right? And the height of the tree is log n, and then thereby the operations that we do like search, insert, and delete, all of them are going to take a log n, right? So log n, worst case, is a better performance, but then we are aiming to reduce too much balancing through the red black tree. All right, well, where is it used? One potential use of red black trees is in the finite maps. And then, if you've heard about sorted maps and tree maps in Java framework, it's been implemented using the red black trees, right? So in Java, every time we use a data structure like tree maps, obj is equal to new tree maps. So it's a data structure. And this data structure is being implemented using a red black tree internally inside the Java framework. So it's really a powerful technique, and popular languages like Java uses this red black tree internally in their code, right? So there are some important properties of red black trees. So every node is colored, right? So a node is colored either as a red or a black color, right? So every node in the tree, if you draw a tree like this, every node is going to have a color, right? And the root node is always expected to be the black color. So which means the root node will always be a black color. And every leaf is a black color too, right? So there's going to be a leaf node, which we could draw up like this with a small square. Every leaf node is going to be a black color node, right? If a node is red, then both its children got to be black, right? So if you have a red node, its children should be black. And then for each node, all paths from the node to its descendant leaves should contain the same number of black nodes, right? So every time you go a particular path like this, or like this, or like this here, all paths should have the same number of black nodes, right? So the black node count should be exactly the same. All right, well, these are some important properties of a red-black tree. If the property is not satisfied, then it's no longer a red-black tree, right? Before we look at some actions like insert and delete, let's talk about some action items here. These action items are related to the so-called balancing act. There's going to be two action items. One is recoloring, which is merely changing the colors, right? So if it's a red color, we may change that to a black color, and vice versa. So recoloring. Rotation is another important technique where we will rotate either left or right to make the tree balanced. So in this particular session, we are going to look at how rotation works, right? So let's look at the rotation procedure. So firstly, left rotation. If you look at the tree that's provided here, we are trying to rotate on X, right? So X is right here. We are trying to rotate that X there, which means X will go down, Z will go up, right? So that's the idea. Every time you're rotating on X, in this particular position, X is going to go down and Z is going to go up, right? So can we look at the new tree? So as you can see, Z has gone up, X came down, and then D is its right child. But one thing to keep in mind, if I can go back to the previous slide, is the right child of Z and the left child of C that you can see right here, the left child of Z, I should say, which is C, will then obviously is going to become the left side of that particular left rotated tree, right? So C here is going to come towards the left of this tree. So you can see that very clearly here. C has moved to the left side simply because it's Z's left child, right? And then X right child. So that's the idea there, is that while we are doing a left rotation, we are kind of adopting the child C and moving it towards the left side right here, right? Whenever we are doing that shift there. All right. So how about right rotation? So if we look at right rotation on Z, Z is going to go down, X is going to go up, right? And then keep in mind, all the right children or right child of X, if there are more children, then so be it, right? So all this hierarchy is going to go towards the right side, right? So meaning it's going to become the left child of Z, right? So that's the idea. So you can see we moved X up, we pushed Z down, and C now become the left child of Z, right? So that's the idea of right rotation. And one thing to keep in mind is that left and right rotations are always symmetrical, right? So as you can see in the slide, once we do left and right rotation on the same position of the node there, then we get it symmetrical, right? So it's going to be symmetrical, and that's an important property that we should all look at. Okay, so can we look at some examples of this rotation process now that we have seen how the procedure works? So let's quickly look at the left rotation on 32. So I'm trying to left rotate 32, which means then we know 32 would go down, 40 would go up, right? And then 37 we kind of adopted and moved to the left side, right? So that's the idea there. So we will see 47, 40 moved up, 32 came down, 37 now become the right child of 32, right? And 44 continued to be the right child of 40, right? So that's the idea there, is that 40 and 44 continues to be the same way, the right child, but 37 somehow need to move towards the left side simply because it's the left child of 40, right? All right, so that's the left rotation on 32. So let's look at one more example where we right rotate on 47. So 47 is right here. So which means then, because we are trying to do a right rotation, 47 should come down, 32 should go up, right? And then all the hierarchy on the right side of 32 should somehow move to the right side, right? All right, so we would need to apply this right rotation procedure. So let's apply that. 32 now should become the new root. So as you can see, 32 has gone up, 47 has come down, and then 40 and 37 would be the left child of 47. 81 continues to be the right child. and then 23, 7, 29 would become the left child of 32, right? So again, if I can go back to the previous slide, you have 23, 7, 29, the left child of 32, that continues to be the same way after we take it up. And then what we are really interested in is in that right child, right? So the right child now would become the left child of 47 when it comes down, right? All the right children. Okay, so that's the right rotation here, right rotation procedure. So at this point, I'm going to introduce the exercise problem, and I like you to work on this problem here remotely and post your solution in Slack to get the participation credit. So I'm saying that before 5 p.m. EST, you can make sure to submit it today, March 25th. If you need additional time, then you should contact me so that we can make an arrangement. I know some of you might be in different time zone, so that is fine. We will make an arrangement with you. So please reach out to me as early as possible if you're not able to do the submission before 5 p.m. today. So the idea of this problem is we are going to try out one. Do the tryout one where we left rotate on 11. So if you look at the tree on the next slide, we have 11 here. Can we left rotate 11? So once you left rotate 11, you will end up with a new tree, and that tree is going to be used to solve tryout 2, right? So tryout 2 is where we are right rotating 18 in that new tree that you had received from the tryout 1 problem, right? So after you solve tryout 1, you get a new tree. Use that tree to rotate 18. So wherever 18 is in that tree, I'm sure there is some 18 in that new tree. So you can right rotate that 18 and then post your solution in Slack. So you're welcome to post the solution either as a hand-drawn tree solution or type down, right? So if it's a hand-drawn solution, then you can simply take an image of that solution and then share it in Slack general channel, or you can also type down the level order sequencing, right? So whichever you prefer is fine. And let me know if you have any questions in this process, okay? I'm sure that you might have more questions while you're doing that. Solving these problems remotely. So feel free to let me know via Slack if you have any questions, or you're more than welcome to schedule a meeting during the virtual office hours as well. So the next step on Friday is going to look at the red blank tree insert, and then we will also look at delete operations this week and early next week. And we should keep in mind that the rotation process is really important, that we should understand that because we would do a lot of rotation in insert and delete, right? Okay, so there's also a reading assignment based on this discussion in Sedgwick 3.3. So when you get a chance, please take over that reading assignment. And if there's any questions, I ask that you would send me a message through Slack, email, and or virtual office hours. I know that it's going to be a little bit interesting and unique for us to meet this way, but based on the situation, we should all feel free to use Slack, email, and the virtual office hours to connect with me if there are any questions. Okay. So, all right. Well, thanks for watching this clip here. And if you have any further questions, I ask that you please reach out to me, either through Slack, email, or virtual office hours, as I said earlier. And at this point, I'm going to end this clip. Okay. Thank you.